very much, Yua, for your kind and generous introduction. I'm very happy to be here. I'm grateful to George for introducing me to this fascinating subject of fractional modeling. Also, he paved the ground for my talk. Really appreciate that. Today, I'm going to talk about fractional large eddy simulation modeling for turbulence. So to cover this subject, I adopt an inverse approach. I talk about the experimental evidence why turbulence is an anomalous transport. And I want to just revisit the idea of large eddy simulation and a very important point that has been missed over the past 40, 50 years, and why fractional non-local modeling is a very promising direction in this area. But before I get started, I want to genuinely thank the organizers of this wonderful event. I want to acknowledge the support we received from ARO, Air Force, and NSF. I want to just especially thank my FMAP group members, one by one, Mehdi, George, Eduardo, Ali, and Hadi. It's been a joy working with this group of hardworking, intelligent PhD students over the past couple of years. Specifically, Ali and Mehdi contributed to the topic that I'm going to cover today. Why turbulence is never Gaussian? I want to start with this question. Well, before I get started talking about that evidence, I want to just highlight that anomalous or non-local transport manifests really in three important things: asymmetric distributions, sharp peaks, and heavy tails when you look at the signals. And really all these three features code the intermittent signals with random long jumps and waiting times often being ignored in a standard transport modeling. So now, if I have a signal, I can readily go and compute the moments of that first, second, and specifically the third moment that basically gives me the skewness and a skewness factor S here, and also the fourth moment that gives me the kurtosis and the flatness factor delta, will be very a backbone that tells me what Gaussianity means. If it's Gaussian, the skewness is 0, which means that my signal gives me a very symmetric distribution. And the flatness factor will be 3, which means that the tails will quickly decay and the tails have no much probability mass to contribute. So now I would like to cut your attention to the most idealistic turbulence, say incompressible flow. I have an uniform flow passing through this grid, and it generates this magnificent turbulence after that, which is we call grid turbulence. This grid turbulence is isotropic and homogeneous, which means that the statistics are not changing with rotations. But now, would you please just imagine this area to be a big ballroom and people are dancing, and these couples from short and skinny to very tall, robust, and shapely, just dancing around. There are a whole bunch of eddies or dancers with different rotational features around, and I want to understand these dynamics. And in order to do that, one of the very first things that we can look into this eddy is to look at the velocity increment. And the velocity increment, it has been shown experimentally that it gives me a skewness factor which is negative for sufficiently large values of R. And the flatness factor also exceedingly goes above 3, which means that in the most idealistic case of turbulence, we do have asymmetric distributions and we have heavy tails. As a matter of fact, this non-zero skewness turns out to be a very essential backbone of the turbulence. We have something called cascade of energy of the turbulence from large eddies to small eddies, from large dancers to small dancers. And that shows itself in Unstrupy equation that think of vorticity, which is the kernel of the velocity, which is a notion of spinning a blob of particle around its centroid. It's basically dot product gives you the Unstrupy, which is the energy of the rotation, how powerful this dance scene would look like. And this first term on the right-hand side that represents the cascade of the turbulence is proportional to S0, the skewness, at R equal to 0. And it tells me that really we definitely need this asymmetry in the distribution for the whole turbulence picture and cascade of the turbulent kinetic energy to go and be basically formed. This is the notion of anomalous transport in the most idealistic case of the turbulence. So now if I have a symmetry breaking case, say a boundary, if I have a boundary layer, think of having a wind over Utah desert. This kurtosis factor at least is 3 and it increases by Reynolds number, which is a notion of inertial viscous forces. And as Reynolds number increases, the distributions become heavier and heavier. And the message, the physical message that can gives us in terms of visualization of turbulence is that high flatness factors, high kurtosis factors are associated with signals which are highly intermittent. And actually the gradients in velocity and later on in scalar turbulence, which are not pronounced in the Kolmogorov theory, are spatially intermittent, which means that when you look at the fluctuations, when you look at the vorticity field, it's very spotty at that small scale. So now, I used to believe that the scalar turbulence is an easy problem. How naive that thought was. It's a very difficult problem. Let's together visit this problem. What are the challenges going on here? So to have that great turbulence, now I'm also interested in understanding the temperature field. And I am just introducing a passive temperature mean gradient. Once I present this mean gradient, you will see that we had heavy tails. Now we have even heavier tails at the presence of this mean gradient. And also these scalar increments become heavier and heavier, while we can see that by distance r between the 2 points. The visualization of the signals doesn't need any justification here. By naked eye, you can see that they are intermittent, velocity, a scalar, and the time derivative. And you can see that we have a noticeable, well-pronounced departure from the local isotropy that is present in Kolmogorov theory, which will be even stronger in the case of a scalar turbulence when you study the structure functions. And then when you look at those, the nature of the fluctuations, and you look at the PDFs, they are anything but Gaussian. So now, think about this as the physical picture of the turbulence for both velocity fluctuations, velocity increment, and also the scalar. But now we know that in a practical problem, resolving all the scales would be very, very expensive. We have the smallest scales in turbulence, let's call it Kolmogorov length scale. And we have the largest fluctuation length scale, we'll call it capital L. The idea of larger simulation, as has been known for over the past number of decades, is to come up with the LES low pass filter. Larger scales are supposed to be resolved and the smaller scales not to be modeled. But now, on the top of that, we have some observability issue, and we have some observable scales, means that really the experimental data that I can get from PIV or can get from hot anemometry really are well above the Kolmogorov length scale. So now really to have an apple-to-apple comparison, my models really need to respect that observability length scale. That's why LES is promising. And really that the application of the low pass filter will further enhance the non-locality. So what we want to do today is to show development of non-local subgrid scale models, which is the dynamics of the subgrid scales that are non-Gaussian essentially. And we want to basically come up with a model that really is able to capture the long-range correlations respecting the non-Gaussian statistics caused by the subgrid scale fluxes. So now I want to cut your attention to these filter advection diffusion equation, because I'm starting with something that originally we'll consider to be a standard. So everything is integer order. I applied as low pass filter, and eventually I end up with this term, which is the divergence of these fluxes. And these subgrid scale fluxes are the closure terms, because I don't know a priori what would be the filter, a scalar velocity minus scalar filter multiplied by velocity filter. So this is the idea how to model this. This is the quantity of interest that even when you start with a local model, you get something like this. This is a kind of a new animal to study its non-local characteristics in here. So to do so, George mentioned of Orsak, I'm mentioning of himself. He taught me spectral methods at Brown. So we developed a 3-dimensional code using pseudo-spectral method, 4th order Rangit with a time integration we basically obtain a high fidelity simulation for both momentum and energy equations. So everything is integer, but now think about it. I'm looking into a quantity of interest, which is these fluxes. The subgrid-scale dynamics is a functional of the velocity field. So now you can see here, the skewness factor again is 1 here, and the flatness factor is about 12. And that's a very pronunciation of non-locality in the context of this dynamics. So this is basically the need. This is the sense of non-locality we are talking about. So now we need to interpret that. We need to say, what do we mean by non-locality? To do so, we derive an evolution equation for the result, the scale, a scalar variance. Not difficult to obtain that. You multiply by phi and just do the ensemble average. This ensemble average, think about it in this context of we do have ergodicity and we have homogeneous turbulence. It's like a mathematical expectation, if you will. And we do have this gradient of the resolved gradient scalar, g tilde I, and you get these terms. This is the evolution equation that you can derive. 3 of them are based on the resolved scale contributions. And I have the mean value of this subgrid scale contribution. That gives me a beautiful hint. Subgrid scale dissipation of a scalar variance. This is the term that I'm looking into. And then again, thanks to a very fruitful conversation I had with George last year about idea of 2-point correlation in the context of momentum equation, but now we can see a similar construction that we can look into the 2-point correlation of the fluxes and the gradients normalized properly. And now, ladies and gentlemen, I want to just show you where non-locality emerges. When I look at the PDF of this new quantity, which is basically this subgrid scale dissipation, you can see that we have sharp peaks, we have asymmetric distributions, and we have heavy tails. And then depending, when you increase the size of your Elias filter length scale to be 53 multiplied by Kolmogorov length scale, you have more and more non-locality. So now if I want to go from Elias to very large simulation, that non-locality cannot be ruled out. So now you have a grade that is coarse, but it's not the end of the story. It's like an Ivy League that blossoms from the middle of that and propagates everywhere. And that can be seen by this 2-point correlation, that how, when you look at the 400 times the Kolmogorov length scale, you can see that that non-locality not only blossoms, but also propagates to far distances. So this is essentially the backbone of the non-locality that we are referring to. So let's see an apple-to-apple comparison. We have an Eddy diffusivity, Eddy viscosity model. We have Prandtl-Smagorinsky model. Usually in the literature, the fluxes are modeled by the gradient of the resolved scalar. And then let's see how this 2-point correlation works. This is the term that we showed how non-locality will be manifested through. You can see that these 2 lines are showing the red, solid, and dashed, solid blue and dashed blue at different length scales. They exhibit considerable statistical discrepancies. And this is indeed the lack of non-locality in the present and current state of our large Eddy simulation modeling. And we are here to show this need and come up with more sophisticated model to correctly capture these calibrations. So this is the work that we recently submitted to JCP, data-driven fractional subgrid-scale modeling for scalar turbulence, a non-local LES approach. And we start by looking into subgrid-scale dynamics. Therefore, the kinetic theory that can zoom in that length scale, that area, would be basically something of interest. So now we have BGK, Boltzmann transport for scalar particles in the context of a standard transport, the equilibrium. So it's consisting of collision and streaming of particles. This equilibrium distribution is basically, in the case of standard transport, Maxwell-Boltzmann distribution. And then eventually you will be able to obtain your macroscopic ensemble average scalar variables by taking the integral with respect to this distribution as a solution to the Boltzmann transport equation. So the creative thing that we do here is to also come up with a generic filtering on the top of this Boltzmann transport equation. So the first thing that you realize is that I have no idea what would be the filtered equilibrium distribution. And I know that it's not equal to the equilibrium distribution when I apply this delta tilde. I need to do modeling, and that modeling is perfectly based on two observations, mathematical approximation and data that we just went through. So the modeling approach is to look at this as a decompose into multi-exponential functions, and multi-exponential behavior is approximated by a power law, which means that I can look at the difference between these two as to be a constant multiplied by a model, and I just set this to be an alpha stable Levy distribution, and this will be my starting point. And then what I would do is to look at the integration of both sides with respect to du, and that after a couple of coffees, of course, we derive without any more assumptions into a filtered macroscopic level advection diffusion equations that has two interesting contributions: the molecular actions, which is local as before, and we have a closure term, and we derive this closure term to emerge as a fractional Laplacian of the resolved scalar field, which means that eventually the model that I'm deriving all the way from kinetic theory to continuum will be a space fractional advection diffusion model. And that is the gift of turbulence. That is the gift of non-locality that LES needed to be represented in the underlying LES modeling. So the cool thing about this model is that I can apply Riesz transform. I can explicitly obtain these fluxes, and I can do this two-point correlation in order to obtain what will be the optimal value of alpha. And you can see that for sufficiently large values of length scales of my filtering in the LES, 41 times Kolmogorov length scale, and 50 times than that, I can get something as alpha optimal, which quantitatively and qualitatively can capture the entire two-point correlation. And this is exactly what George emphasizes on. Fractional modeling is expressive. It gives us this flexibility to not only capture this inherent non-locality in the subgrid-scale dynamics, but also it gives us a really nice way of performing the simple minimization in order to get this alpha. And by the way, alpha is deviating from 1, which means quite a strong non-locality, as I depicted in the motivation slide for the scalar turbulence. It's a very strong non-locality that is captured by a single beautiful parameter alpha as the index of fractional Laplace. Not only that, you can see that it gives it performs much better than the corresponding apple, which was the Smagorinsky model, in capturing the tail of the distribution. You can see that fractional model does a much better job on both sides of the distribution and is basically respecting the non-Gaussianity of the subgrid dynamics. So now that was for the scalar turbulence. What we do for in the context of Navier-Stokes equation, because now the whole literature developed for subsurface transport phenomena. Mark Bierschot wrote a book on this subject, and now turbulence itself, the background noise looks like a porous media that is dancing all the time, and it's evolving in time. And now that dynamic leads to also fluid, basically fluctuations that requires some attention here. So Navier-Stokes equation, F equal to ma, nothing anomalous in the context of that. But now, again, I'm dealing with subgrid-scale shear stresses, adopting a similar approach, starting from kinetic theory of Boltzmann transport. But the dedicated matter here is that I get 3 terms: pressure gradient, local viscous terms, and also similarly a fractional Laplacian of the resolved velocity field. So we have basically applied, we showed that both formulations are rotationally invariant, Galilean invariant, and they both satisfy the second law of thermodynamics. And then by performing quite simple optimization, linear regression, we will be able to see that how this alpha that can basically code all the non-locality, not all the intermittency through itself, is a function of the LES filter length scale and the Reynolds number. And you can see that this alpha will be able to single-handedly capture all the non-locality that basically respects all these two-point correlations and basic Karman-Howard's two-point correlation that George mentioned about as well. So I want to just end up with this summary and conclusion that we constructed a high-fidelity subgrid-scale scalar flux database for DNS. That was a separate submission we did. It's available on arXiv. We came up with a very meticulous statistical interpretation of non-locality in the subgrid-scale dynamics, both scalar and velocity fields. And we developed two fractional order subgrid-scale LES models starting from Boltzmann transport framework, and we introduced a rather easy and a cheap way of performing data-driven calibration of the developed non-local subgrid scale models. What we are doing currently is to perform a systematic a posterior study on the top of the a priori studies that I just went through. We are examining more complicated form of subgrid scale models that leads us to tempered fractional Laplacians and distributed order fractional Laplacian. And we really aim to apply them in the context of more complicated turbulence, including anisotropic turbulence dynamics in the basically data-driven framework. On that note, I hope you enjoyed the talk, and I stop here. Thank you very much for your attention.